So I wanted to make a quick video and talk to you a little bit more about sigma bonds and pi bonds. Make sure you can look at a structure that you have drawn or one that has been given to you and make sure that you can count up the number of sigma bonds present in the structure and the number of pi bonds present in the structure. If we look at this structure here, this is a molecule called ethylene. We have a carbon-carbon double bond in this structure, and each of our carbons also has a single bond to the hydrogens. This is a molecule whose structure you'll get into in a lot more detail as you go on to organic chemistry. This is not a structure that I would ask you to draw simply because it doesn't have a central atom. The structure is a little bit more complex than that. But as we look at this model, we have that carbon-carbon double bond, and we have our single bonds between the carbon and the hydrogen. So one model of this structure looks like this. This model is very similar to the structure that we draw on paper. And if I turn the model like this, you see that carbon-carbon double bond in the structure. But the model that's a little bit more descriptive of the actual structure in three-dimensional space is my model that looks like this, where in this particular model, one of my carbons is here, my other carbon is here, and these white groups represent my four hydrogens in the structure. Now, the gray bond here that is shown, this is the first bond between my carbons, and this is the sigma bond in this double bond. So this is my sigma bond. The second bond that forms between my carbons forms between my parallel and unhybridized p orbitals that you see here. So when those orbitals are parallel to one another, they're able to share electrons by forming an overlap above and below that existing sigma bond. So that overlap looks a little bit like this, where if I use this black rubber band to tie those unhybridized lobes together on this side of the structure, and I can use a second rubber band here to tie these lobes of my orbitals together. And that looks much like what my pi bond is in three-dimensional space. My unhybridized p orbitals that are parallel, they must be parallel in order to have this overlap above and below that existing sigma bond to allow me to share a second pair of electrons between my atoms. The first two electrons that are shared between my carbons are shared in this sigma bond. The second two electrons that are shared between my carbons are shared across the four lobes of my unhybridized p orbitals and the two areas of overlap above and below that existing sigma bond. So that in this structure, you see that we have four sigma bonds to our hydrogens. 1, 2, 3, and 4. We have our fifth sigma bond here between my two carbons. This sigma bond is formed using my carbon's sp2 hybrid orbitals. And this pi bond, so the one pi bond that I have in the structure, is here, shown with the rubber bands, and it is where my carbon uses its unhybridized p orbitals to share additional electron density. So that if I'm looking at this structure, I have a total of 1, 2, 3, 4, 5 sigma bonds and one pi bond in the structure. So if I look at the structure of acetylene, where I have a carbon-carbon triple bond, this is again not a structure I would ask you to draw because it's more complex than just having a central atom, but this is a structure you should be able to look at and understand the connectivity as well as the bonding that takes place. We see in this structure that this carbon has sp hybridization because of its two electron groups. Same for this carbon here. My hydrogens never undergo hybridization because they only have one orbital to bond with. So that if I look at these carbons, this triple bond is made up of one sigma bond and two pi bonds. Remember that the sigma bonds are made with our hybridized orbitals, and the pi bonds are then made with our unhybridized and parallel p orbitals. So that my model for acetylene looks like this. Here is my carbon, my hydrogen, and my hydrogen. So my hydrogen, carbon, carbon, hydrogen bonding pattern. And then we have our parallel unhybridized p orbitals that are going to allow me to make the double bonds. So I have one set of parallel unhybridized p orbitals right here. So I have 1, 2, 3, 4 lobes for those p orbitals. And I can show the overlap of those p orbitals, like this, so that that overlap in front and behind that first sigma bond gives rise to my first pi bond between my two carbons. If I need to put additional electron density between my carbons, those electrons have to go somewhere else. I already have the electrons directly between my structures. I already have electron density here and here, so that my next pair of electrons to be shared is going to occur between these four lobes of my unhybridized p orbitals. And so to show that, I can put the rubber bands on at this position, and this position to show that additional overlap between my parallel and unhybridized p orbitals. Overall, in three-dimensional space, this is what my structure looks like. So that in this structure overall, I have 1, 2, 3 sigma bonds and 2 pi bonds, one with the tan rubber bands and one with the black rubber bands.